We're just going to hit the big highlight of chapter 1.2. There's no 1.2 homework, although I really recommend that pure math majors read through chapter 1.2 in some detail and then come back to it later in your career. So we're just talking about the formal definition of what a limit is. So if someone writes that the limit as x approaches c of f of x equals some L is a y value here, if that's true, then that means that you can guarantee that the y values are within some tolerance of this y value by keeping x within some related tolerance of that particular center point there. So if you were running a manufacturing process and you said, I need to keep the length of whatever part I'm making within some tolerance, and I can do that by keeping the temperature of the metal I'm working on within some input tolerance. That's kind of the theme that's going on here. So here's a graph of it. The kind of game we're playing is, if someone specifies an output tolerance, you can come up with an input tolerance that guarantees that the output will be within that tolerance. So as long as the x value is in this interval, the output tolerance, the output value will be within the tolerance bands shown there. So let's go see this in Desmos. So here we are. I've got f of x equals square root of x. I'm centered around the value x equals 4. And I've got a tolerance band around y equals 2 here. I'm trying to show that the limit of square root of x as x goes to 4 is 2, which seems fairly straightforward. And the book shows all the algebra for this. So the idea is, as I shrink the tolerance on the output value, get a narrower and narrower band around what I think the limit is of 2, there's a systematic way to determine a band around the x value such that the output curve is always between the green upper and lower limits here. What is that relationship? The book shows all the algebra of finding that it's this. That is a shortcut way. That's the Desmos way of writing the Greek letter epsilon. So because there's a nice relationship where the more I shrink the output tolerance, I can systematically match that with the input tolerance as the tolerance goes to 0. That shows that 2 is the limit of square root of x as x goes to 4. What if I thought the limit of square root of x as x goes to 4 was 3? Then even at large tolerances, I can see that the red curve goes outside of the green horizontal lines, the green vertical tolerance. And so that shows that 3 is not the limit of f of x equals square root of x as x goes to 4, because the red curve is going outside the green lines. So our next question, what is the limit as x goes to 5 of sine of 1 over x minus 5? It's not a bad idea to draw that. Here's 5, but we're going to lose track of it pretty quickly. Sine of 1 over x minus 5, as you come in this way, ends up oscillating faster and faster, infinitely fast as you get close to 5. And as you come in this way, it ends up also oscillating really, really fast. And it's always between plus and minus 1. And the question is, you might say, well, it's always between plus and minus 1. Is this limit equal to 0? Because it's getting near 0 infinitely often. But then it's going farther away from 0. It's oscillating without settling down to 0. Let's go take a look at it in Desmos. So here I've got sine of 1 over x minus 5. I've got my central value of 5 on the x-axis. And I've got a tolerance band for the y values. And we think the limit might be 0. And then if I shrink the tolerance around y equals 0, can I guarantee that the red curve does not leave this green tolerance band by making this blue band on the x narrower and narrower? Well, no matter how narrow I make it, that red curve is always going to go up to plus and minus 1 within some very, very tiny amount of x equals 5. So I can't guarantee an output tolerance by restricting my input tolerance here. So that means that the limit just does not exist. 0 doesn't work, nothing else works. the function just keeps oscillating without settling down, where if I put something like x minus 5 on it, then the function gets smaller and smaller, and I can keep it contained between my output tolerance by, I would have to adjust my input tolerance, but we're not going to worry about the exact mechanics of that. So that means that for this function it oscillates, but its amplitude goes towards 0, so it is settling down fast enough, and 0 is the limit. So that's the highlights of chapter 1.2, just the definition of limit, about making sure you hit an output tolerance by specifying the related input tolerance. Let's go write our conclusion on paper, because exact phrasing is often important. So we learned that this limit does not exist. DNE means does not exist. Because we can't guarantee a tight tolerance for y, by zooming in on x, a tight tolerance for y, any better than plus or minus 1. Like, sure, you can keep it to plus or minus 1 rather than plus or minus 10, but you can't keep it to plus or minus a half in the y-axis. All right.